Hello and welcome to the STEMC Studio channel. In this video, we will be making the final preparations to get our geometric number for the Euclidean plane ready for applications. There are two things that we should take a look at. One is the string representation of our complex number is not very compact, as you can see down here. If I were to replace, for example, the scalar part, or any of the parts indeed, by 0, then I still get a long string, and it would be much nicer, for example, if that was just 0, plain old 0. Likewise, if I had just a vector with the value e1, then I'd like that to be more readable. I'd like it to just say e1, not 1e1, as it does there. So by being more compact, we make our mathematical notation, we make our application more readable, and that's good for people who are trying to understand the systems that we've created. The second thing that we should do is we should improve the testing that we have to ensure that we've got proper coverage for the different products that we have in geometric algebra. So most notably, we have the exterior product, the scalar product, the left contraction, the right contraction, and then the geometric product. So you will have already seen these tables before and in previous episodes, and you'll know like how to implement them and how to write unit tests for them. So we won't go into that anymore. But let's get started on the toString method for the representation and see how that goes. Okay. So I've set things up here so that we've just got a printout of both a plain text representation of the geometric number and a LaTeX representation of the geometric number. From just playing with it, I've kind of come up with an informal set of specifications, and also in actually implementing this, some experience trying to implement this in the past. I've also made some recommendations here that I'd essentially keep this thing fairly simple in this first iteration. And I think it'll be actually plenty good enough for everything that we want. So one consideration is handling negative components without a redundant plus sign. So for example, if I have a -1 in here, then I don't want to get plus -1 or minus something times e1. I just want to get minus e1, okay? So that one's fairly straightforward. Hide components with coefficients equal to 0. Well, you can see that we've just definitely not got that going on. Have both plain text and LaTeX variants, so we can use one just for simple debugging, where we may not want to have the LaTeX, and then we can use the other one where we have LaTeX in situations where we've got some kind of LaTeX processor, such as MathJax, that can produce nice output. And that will be the case, for example, if we have JSX graph here, or if we're writing out to a document object model here where LaTeX is loaded and we can use it. When all the components are 0, the fourth requirement, when all components are 0, we'd like to just render the value 0. So, you know, we want basically this string, instead of having this string, to just be a single 0. There's nothing really special. In fact, 0 is kind of a very universal number, because if you multiply something by 0, it's 0. So the symbol 0 is perfectly good enough. We don't need to adorn it and decorate it. We'll make it the vector 0. You know, this is a multi-vector. It has to apply for scalar, vector, bivector, all of those parts being 0. So we just call it 0. The fifth requirement here is optimize the notation when the coefficients are equal to either plus or -1. So if I have a +1 in one position, say a -1 in another position, these ones should just really, the 1 is not required. It should be just plus e1 minus e2 in this situation. When obviously the numbers become 2, or some other non-1 number, then you do have to have that. So 1 is kind of special, and 0 is sort of special. We need to pay attention to those. And then the final thing note I've made is that I think we should omit white space just for simplicity. If we do want to have white space, then we will find ourselves probably having to essentially kind of like decide when does white space fit in, and we will be kind of like almost kind of like, you know, formatting this thing, and that's going to be extra kind of like complication. It's certainly doable, but I think that we should do it without white space to start with. Okay, so as you can see, I have set up toString and I've set up toLatex. In fact, toString, to be honest, is sort of defined on a JavaScript object. And even if it wasn't in our code, and I've set it up in our code, even if it wasn't in our code here, we wouldn't actually know, other than the fact that it wouldn't execute. Okay, but I've set us up here so that we've got both these methods, and I've left the original implementation in here. A little bit more space, so we'll hide the docs and we'll stop it running. You've seen it. I've left the original implementation in, just cleaned it up a little bit for toString so that we don't have the MathJax type stuff, the LaTeX stuff in there, and we're ready to go. So here's the sort of template that we need for toString. It's just like the other ones, describe, and then we have a function that gets called, and then it is where we define our expectations, and then inside those we're going to have our expectations. So let's run this, and let's run specifically the tests. And you can see toString, actually it's reporting that the spec has no expectations because we don't. Okay, so we can start off with something like, let's expect that, and we'll just construct our geometrics on the fly, 1, 2, 3, 4, say, and then we'll call toString on it, and then we'll say to be, and what do we want this to be? 1, oops, need some quotes. We want this to be 1 plus 2 E1 plus 3 E2 plus 4 E1 wedge E2, right? So basically we're not going to have white space, and we're not even going to put in, we could put them in multiplication signs here, but I'm actually going to not do that so that it kind of makes our LaTeX implementation more similar to our toString implementation right now, at least, and that will just make it simpler to develop. Over time, if you feel like you want to have multiplication symbols in the plain text version, then you can go ahead and do that. So here's our very first test, and it's really, you know, really for a first test, this is more than what you might have, because we're actually asking it to do something fairly significant here, rather than just checking, for example, that this exists. But since that's so trivial, I'm just gonna not even do that. Okay, so we're not passing, so let's go to the implementation. And we see that basically we have a white space problem now, because I said that we're going to drop white space. So that's what we will do. And I'm even going to drop it in between the wedge symbols in here. And it works. Okay, great. So let's remind ourselves what's next. Next one is about handling negative components. So let's go and create that spec. So the expectation. Oh, yeah. Okay, do we want to have a nested describe here? You know, you could do, I think sometimes you have to kind of like just go with, you know, go with something and then decide whether it makes more sense to sort of refactor it. So we have minuses. We want to have a minus sign here, a minus sign there, minus there, and a minus there. Okay, and let's get rid of the documentation. Right, so we've got minus, and there's our redundant stuff. So negative coefficient, so I'm just going to describe this, should I think I'm going to reword this, toString, so it reads as a sentence, toString should not have redundant plus signs for negative coefficients. Okay, that sort of says it right. And I don't have a description for the first test. And it's actually doing quite a lot, actually. So let's just say should I'm not quite sure what that one should be just yet, so I'm going to leave it. All right, so here's our test. We've got a problem with the coefficients. So right-click on toString, go to that guy, and what we need to do here is we can't just be sort of jamming in a plus here, because we don't know, this thing might be negative. So the approach here, I think, has to be that instead of assembling the string like this, we should assemble it sort of in parts and then check each part as we go along and say, what do we need? So let's try something like this, const, and for want of a better word, we'll call it parts, whose type is a string array, and it's initialized to the empty array. And then what we can do with our parts is we can return parts dot, and then we just join all of the parts together with no spaces. Now that's complaining because there's a return just before. Okay, so yeah, now we got two failing tests, so we better put everything back. Actually, let's just bring that back as a comment just so that we can look at it. So you can see that really all we need to do is just to simulate what we had before is do like a parts dot push dollar this dot a. I'm going to do that for each of the components. This dot a, this dot x, this dot y, this dot z. And actually, oops, not ZB. And then actually what we want to do is we want to take control of the, of the sort of the plus and minus symbol. So I should perhaps have gone math.abs, this dot a, dot abs. So we take the absolute value. So that means that we're only going to get things without signs. And now actually the problem has sort of flipped, because rather than, well, it hasn't flipped. I mean, we have to put in both a plus and minus sign if it's appropriate. Okay, so parts.push a. So okay, let's go back. We got 1, 2, 3, 4. Obviously what we need to do then is make this look a little bit more like it was before. So parts.push. Now I'm just going to go for what we had before to start with. So we're going to add a plus there. Like it's a plus between everything, right? So, and then we're going to have some multiplication going on. So in here we need to have an E1. And in here we want to have an E2. And then finally, we need to have an E1 wedge E2. Okay, and actually I noticed on the right-hand side, so our we've only got one failure now, which is our last failure to do with a negative number. So you can see now this is kind of close, except the pluses in some places should be minuses. So what we want to have here is if this, oh, right, I need to also do it for those first ones. So if this dot A is less than 0, I'm just thinking here about the case when when a particular coefficient is the first term, and in that case you don't want the plus sign. Well, we'll see. I'll show you what I mean. You don't want the plus sign if it's like the leading coefficient. So in this case, the plus happens because we want to, if this dot x is you know what? I think what we want is we want to say if this dot x, I'm going to sort of try to capture the whole idea here, which is the reason for the existence of these whole sections is because of the various parts being non-zero. I was just kind of like starting to see that I was going to end up with conditions that you might just have to like follow me sort of through on this one. And here, just to make this kind of correct, I'm going to go this dot A, or rather consistent, then this whole block. Okay. All right, so yeah, we still only got one breaking test, and we start with -1 that agrees, then it's this bit. So if this dot x is less than 0, then we want to push onto the parts a minus sign. Otherwise, we want to push on the parts a plus sign, I think. So let's see how we're doing. -1, -2. I mean, that looks like it's kind of like going the right way, I think. So same thing for here. If this dot y is less than 0, then parts dot push the minus sign. Otherwise, you can have a plus sign. And 1 - 2 e1 -3 e2. And I think the last one should do it for us. So let me just format that. In fact, I'm going to grab this bit because it's the same code, which is starting to suggest to me there's a common function here for each component. Although the scalar part is looking, it's just a little bit different. But maybe, yeah, it's a little bit different because it doesn't have this basis part. It's not the fact that it's leading, but that could have an effect. Okay, so we have done this spec. We don't have redundant plus signs for negative coefficients. So what was next? Hide components with coefficients equal to 0. So let's have a test for that. So this one's pretty easy. We could do this. Let's kind of like just do it all in one go. So we could do it by doing each one in turn. But I think we're just going to go with this. And in fact, the answer that we want it to be then in this case is we just want it to be a single zero. All right. So we want to hide coefficient. It should return, so toString should return 0 when all coefficients are 0. There we go. So there's our test for our test-driven development. And oh, that's kind of interesting because of the code that I put in before, where we're testing each one of them for truthiness, which is basically non-zero value. We're actually getting no parts. We get the empty string that gets joined together, and we get nothing. So I think the answer here is just if parts.length is truthy, then we'll join them up that way. Otherwise, we will return 0. And yeah, that worked. So let's just format that. Okay, great. So seems we're good. What's next? So there is a LaTeX one. I'm going to leave that one out just for a minute because I think this is sort of out of order actually. I think it'd be better to do this common thing because this is it cuts across plain text and LaTeX, avoiding the one. The white space is already there, so I guess I could have reordered this. So put a LaTeX at the end, maybe. Yeah. Okay. So we need to optimize the notation for plus or minus 1. So let's close the documentation. Go to our tests. And let's do the case. Let's do plus 1 first. Should optimize coefficients for plus 1. Now, the way this optimizes will be a little bit different for the scalar part than the other parts. So anyway, let's kind of give it a go. So let's try all ones. And what we want here is we want it to be 1 plus E1, 1 plus E2, and 1 plus E1 wedge E2. Okay, yeah, so we've got this test where it's sort of different, except perhaps the leading term. Perhaps I should have made this, yeah, I'm going to just change this test, 2, 3, 4, 5, 2, 3, 4. What I want to do is not have the overlap in these two tests, so I'm making this test not cover the case when we have 1. So this will be different, so we get value out of the different tests, and we don't have the sort of repetition. Okay, so we expected 1 plus 1E1 plus blah 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 to be that. It just should be abbreviated. So we go to our code, and the scalar bit we don't care about, but the X and the Y and the B bit we do care about. So we are just going to just drop this. There's no extra complication from having multiplication signs. So we're just going to go if this dot X is equal to 1, or if it's not 1, then we'll do that. And so that got rid of that one. So same thing for Y. Do Some of you may argue at this point that that perhaps should I have had separate tests so they would have failed in each part. I guess because my strings are showing all of the parts, then it is actually testing that I've done it for every coefficient. So I think this is good. So 1 plus E1 plus E2. And in fact, it's just really the last bit, the B, that needs fixing. So if this dot B is not equal to 1, then render it. And now I'm just thinking about the -1s, and it's almost like this math.abs could sort of come out, and I could compute it once and then just do it down here. Then I wouldn't have two conditions. Anyway, getting ahead of myself a little bit because that's the next test. But let's do this. We're good here. Let's do the -1 case. Looks like I've misspelled some coefficients. Okay, there we go. Coefficients. There we go. You guys must be kind of cringing watching me type sometimes. All right, there we go. -1. Let's put -1 in here. -1, -1, -1, and the result should be -1, -E1, -E2, -E1 by G2. And breaking on this one because we need to optimize it out. So right click on that, go to definition, here we go. Right, we don't want to do it for the scalar part too. So the reason we don't do it with the scalar part is because we're not multiplying it by something, like by the E1 here. So, okay, so I'm going to do it. I think what I'm going to do is I'm going to pull this out. So I'm going to take this const. Actually, what I should do is like create a variable that's not x, but in fact abs x, I think would be better because that way it makes it clear. And then I'm using abs x here. And then what I want to say, if the absolute value of x, okay, never mind. Oh, okay, good. Sorry, I was wondering why we had multiple failures there for a second. Just format. So let's see. Yeah, looks good. We got rid of the -1. It's just -E1. Okay, so same thing down here. So I should be careful. Always a danger when you copy things that you don't change everything. So I'm going to be a little bit pedantic there. Just check out abs y. If abs y is not 1, then push abs y. Okay, just saving myself a tiny bit of processing by not recomputing that twice. And yeah, now we're just on the last one again. So abs b here, abs b, math.abs b, abs b is not on. Need to drop abs b in here. How are we doing? Okay, good. So you know, looking pretty good so far. Yeah, there's obviously a lot of commonality between like b, y, and x are actually very similar. The scalar part is different. Don't really need this comment anymore. Scalar part is different. I think if there were more coefficients, I would be more inclined to make. Well, I should refactor this, shouldn't I? Because let's just hold it. Let's just hold off just one second. I can see that what's gonna happen is that we will want to borrow this for this, and when we do that, this whole function should be pulled out. Okay, so all right, let's go back to our situation here. So the last one, well, let's make sure we've done the negative component handling. We've done the all coefficients equal to 0. Yeah, these ones almost kind of combine themselves. Optimized notation for plus and minus 1, we've done that. We've built in this one, we're just not doing white space. Have both plain text and LaTeX variants. Okay, so to do the LaTeX test, so since we're doing LaTeX now, then I should write a LaTeX spec, right? So question is, do I need to test the whole of LaTeX, or should I just check what's different, which is the basis vector? It's quite possible that in some ways I don't really need to do the whole of LaTeX here, since these are kind of like common. Yeah, let's well, I'll decide in a minute. I'm just going to comment these out for the time being. A little x. The x basically disables the test, so you don't see it in the failures. All right, so if we're doing this 1, 2, 3, 4, basically this needs to have an underscore and a curly brace. E2 needs to have the underscore and the curly brace. Let's hide our docs. And oops. E1 needs to have an underscore and a curly brace. And E2 underscore curly brace. So we've got a failing test now to LaTeX with a sort of fairly simple case 2 plus 3. E1, 4, E2, 5, E1, wedge E2. And it looks, well, actually it looks, yeah, it looks like mostly we're just lacking the LaTeX stuff. Let's see. I don't know why that looks like it's got, no white space. Who can say? All right, so let's not worry. So what I need to do is I want to rather borrow this whole implementation and use it for this LaTeX, but then just pass in different basis values. Yeah, because the wedge is in here, I don't need to pass in a separate wedge. That's going to be part of the basis. Okay, so what I'll do is I'll make a function out of this, toString, that whole thing, and I can drop it right in the same module and call it function. There we go. Function toString. Got some errors here. Okay, we're not using it yet, that's obvious. And yes, we're outside the scope of the class. Also, we're missing all of the thises and stuff like that. So what I'm going to do here is I think I'm just going to pass in the coefficient values. So that we have these. And actually, you know what I should be doing here is, since I'm actually refactoring my toString function, I don't really care about that. Well, we're working okay, but we're not using it yet. Okay, so and then here, yeah, it's probably a more efficient way to delete this dot. Okay, I'm going to use it just to give you the idea here. So I'm going to return oops, return toString of this dot a, this dot x, this dot y, and this dot b. Okay, I should have done that so you could see what I was attempting to do. So basically I'm pulling out this toString function, and then I intend to reuse this to parameterize this toString function with an extra parameter that will take into account the different basis vector parts. Okay, so let's fix this to get our tests working again. And it should be as simple as looking for all of these places where we've got this dot. So just remove these. Talk amongst yourselves, as they say. Okay, nearly there. We done it? What's wrong? Okay, something wrong. Oh, this dot B down here. Are we good? Yep, we are. A little bit of white space at the bottom. So we are running again. Our toString method is working again, and we can now start to visit the toLatex. Or actually, I guess what we should do is we should kind of like continue to refactor this toString so that we can pass in the basis parts, and then we can do the other ones. So what we want to do is we want to sort of pass in something that looks like, say, an array with 4 parts in it, one for each basis vector. So this is E1 wedge E2 for the last one. Not sure whether we need anything for the first one, but I'm going to do that. Let's hide that for a minute. So that's what we want to do. I'm not sure this is the first one will ever get used. Maybe this should be the empty string. Not quite sure. Let's go to our toString method here, and we are going to have a parameter. What should I call it? I'm just going to call it. I could call it basis string or something like that. But that would, just not using it, that would be a bit long and wordy. I'm just gonna leave it as basis. Maybe I can put a comment in here. That's what I probably will do. What I could do here is, rather than just saying this is a string array, I could be a little bit more explicit and say this is an array that consists of exactly 4 strings. Okay, so that will just force me to use it correctly. And then this down here is basis of 1. So the 0th component is 1, so we don't use that. This is basis of 2. That, I'm still working. And then this is basis of 3. Okay. Actually, almost suggests here that if we had the absolute value of the scalar part, we could sort of incorporate this 1. I mean, it's doing the same. It's not doing anything special right now. Let's leave that functionality for later. So we are still working, but now we've got the refactored parameterized function. So implementing the toLatex now should be kind of trivial. So now we're going to try this guy, and it should be basically 2, 3, 4, 5. Should be the same thing, but with the appropriate underscores. So toLatex needs to essentially be the same call, like that, except that I need to pass in the underscore squiggly 1 to you could argue actually here that for this parameter we don't really need, you know, we've got E1 here, that really should define what this is, but we'll maybe save that one for the future. So we want to have a wedge in here. What went wrong? Oh, did I not change over? Right. Oops. Should. The dangers of copying and pasting. Okay. So we expected 2 plus 3 e underscore 1 plus 4 e underscore 2 plus 5 e underscore 1 to be. Oh, okay. So we want this to be wedge like that. Yeah. And I suppose just as a sanity check, we could go look at our output here. Uh-oh. Got a leading plus. Leading plus. Right. So, oh, right. So basically, we only want to have a plus if the parts, if there's something coming before. Otherwise, we don't want to have the plus, at least for these final coefficients. So let's write a test for that. In fact, this is actually the general case. Nothing to do with it being 1 or anything like that. So bring back our tests. There we go. This one should omit plus sign for leading. I mean, this is really, this should be a describe, shouldn't it? So I'm going to do something here. I'm just going to copy that, paste it in there, format, and then turn this into a describe. Because I'm actually going to do yeah, so not sure what my description here. I want to basically say here that when I've got no scalar, then I want to have that. Yeah, let's get this working first. I'll think about this description here. So the whole point is we don't want to have the E1 term toString now. Yeah, we don't want to have the plus. We only want to have the plus if there are existing parts, right? So I think it's just if parts dot length, then push a plus. Yeah, there we go. I suppose that's correct. Right, so let's carry on with the specking. So what we want to spec out now is, let's spec out the case where this one is also 0. So this will be the leading term. We want to get that, and instead we get the plus. So now we want to go to here, and we want to do the same with y. The plus should only appear if parts dot length. Then we'll do that. Almost good. So keep going here. So the description here is so yeah, it's described, so it shouldn't have should. Describe toString when leading coefficient coefficients are 0, toString when the leading coefficients are 0 should, this is not coming out too well, should I'm just going to say should handle scalar 0, should handle E1 0, and then the next one, it should handle E2 0. So I'm going to put a 0 in here, and that should give me 5 E1, E2, and I've got the plus again. So got to do the same thing with the if parts dot length is truthy. In other words, if there are parts already, I need to push A1. Okay, let's format that. Let's go back and look at our implementation here. So 2E1 minus 2E2, 2E1 minus 2E2. I mean, so one of the things you often find is like when you run your implementation, you can sometimes sort of cycle through new ideas very quickly and find new test cases. Let's just run through a few things here. That's looking pretty good. Minus E2 looks good. 0. Here's just 0, 1. E1, they're looking pretty good. All right, let's go back. I think we're done. Yeah, I'm pretty satisfied with this. Yeah. Okay, so I think we'll actually call it a wrap there. We've made it pretty compact. So that was interesting. A fair amount of a little bit of trial and error there. I guess if I went back and revisited this and spent a little bit more time doing analysis, I would probably find maybe some ways to sort of refactorize that toString method. I think certainly there's a common function in there that could be pulled out, and there may be some other kind of optimizations. But this is a fairly reasonable illustration, I suppose, of a top-driven development approach. Of course, that doesn't mean to say that you wouldn't be working with like a pencil and paper on the side, just thinking about it maybe a little bit more theoretically, a bit more carefully. But I'm somewhat constrained by trying to produce the video and show it working. I hope you enjoyed it. We are ready, I believe, to use our multi-vector in real applications, and those applications, I think you're going to be kind of like blown away if you've not seen a geometric number being used to do something like reflections and rotations, and some of the ways that it can kind of express geometric relationships. Then I think you're really gonna enjoy it. All right, if you like this video and you want to see more, please hit the subscribe button below and hit the like button if you like it. Every time you hit the like button, it lets me know that somebody is interested in, and that makes me want to do more videos. Take care, happy coding, see you in the applications. Bye-bye.